Trig equations, type 2 highest common factor. So earlier on in the chapter we were looking at solving trig equations either by reading off values from our trig graphs or using a given equation where we just had a single trig ratio on the left, a number on the right, and then we were either getting cos inverse, sine inverse or tan inverse to solve for theta. So we're going to look at three more types today now after everything we have learned from page 14 and 15 in our tables. And the first one we're going to look at is highest common factor. So the example we're going to look at here is from the 2003 higher level paper, question 4b, where we were asked to find all the solutions of the equation sine 2 theta plus sine theta equals 0 in the given domain that theta has to be between 0 and 360 degrees. In other words, within the first four quadrants. So we've just finished some difference to products, so you might end up looking at this one as using the formula sine A plus sine B. And of course that will also work for an answer. But I'm going to look at this as being a double angle here, where we have sine 2 theta. And sine 2 theta we know from page 14 is 2 sine A cos A. So that means I can write that as 2 sine theta cos theta plus sine theta equals 0. And now I can see that I have something common, sine theta and sine theta. So if I take out my highest common factor there, sine theta, that leaves me with 2 cos theta plus 1 is equal to 0. So if I put a bracket around my sine theta, what that basically means then is that we have sine theta multiplies by 2 cos theta plus 1 to give you 0. So that means that sine theta, that means that sine theta must equal 0, or 2 cos theta plus 1 must equal 0. So if we work with sine theta equals 0 first, well, that means that theta must equal sine inverse of 0. And you can, of course, use your calculator, making sure it's in degrees, because obviously we're given our domain up here in degrees. That's really important. So the answer has to be in degrees. Could be given to us in radians, but here it's degrees. And we're looking for sine inverse of 0. So if we go to page 13, we can see that if I'm looking for sine inverse of 0, well, that gives me 0 degrees, but it also gives me 180 degrees. And of course, if I'm looking at the unit circle here, well, 0 is also the same as 360 degrees. So I've gone around 0 and back to 360. So therefore that means that my answer for sine inverse of 0 can either be 0 degrees, 180 degrees, or 360 degrees. And that's why I always prefer to use page 13 in my maths tables, because obviously it's telling me that from my table, where if you put it into your calculator, you'll just get one answer, you'll just get 0. So now I need to look at the second part of the equation, which was that 2 cos theta plus 1 is equal to 0. So basically that means if I get cos theta on its own, well, cos theta is equal to minus a half. So now we have to get cos inverse. And we always get cos inverse of the absolute value. And we have to remember our unit circle here. Okay, so if I look at the table there on page 13, I can see cos inverse of a half. Well, there's a half, must be 60 degrees. So in other words, this is my reference angle, 60 degrees. I'm going to use that then to figure out all of the possible values that would give me minus a half. So we have to remember from our unit circle, all so terribly confusing. So first quadrant, second quadrant, third quadrant, and fourth quadrant. So we're looking at cos here, and therefore we're also looking at it being minus a half. So where is cos negative? Well, cos is negative in the second quadrant and also in the third quadrant. So even though I've gotten 60 degrees here, this isn't actually one of my answers. It is only my reference angle. I'm referring to my unit circle and I'm applying the rules for each quadrant using this 60 degrees. So my second quadrant rule, is that it must be 180 minus theta. So the reference angle is 60. So 180 minus 60 is 120 degrees. And in the third quadrant, the rule is 180 plus theta. So 180 plus 60 equals 240 degrees. So therefore, my answer for cos inverse of minus a half is in fact 120 degrees and 240 degrees. So I do not include the 60 degrees unless it was a positive ratio, but it wasn't. It was minus a half. Okay? So, therefore, what is my answers? So, I have two sets of answers. So, I just finish off by saying, therefore, my solution set for theta, and I list all the possible answers, and I tend to put them in increasing order. So, was 0, 120, 180, 240, and 360. So, they are all the values that will satisfy this given equation of sine 2 theta plus sine theta equals 0. Okay, and as I said, you could in fact use this one down here as well, where we had sine A plus sine B. That would also work, but we'll come up with that in the next type. So on your sheet, you're going to look at exercise 8.4, and you're doing question 1 to 4, and you're doing 8, 10, 14, and 21. You can do them all at the end of the video. So type 3 is where we're going to use our sum difference and change it to a product. And the example we're going to look at is from 2008 higher level question 5b. So again, our sum difference to product is the bottom of page 15 here in our tables. So just to remind ourselves, so they were the last set of formulas that we were looking at from our list of all of our proofs. We didn't prove these, but we were looking at using them. So this is one of these other uses for them. So the first thing it says here to do is to write sine 4x minus sine 2x as a product. Okay, so we're going to take sine 4x minus sine 2x. We'll write A over the first angle and B over the second angle. And this is to help us identify which equation we're going to use. So we're looking for sine A minus sine B. So that's the last one here on our list on page 15. So in other words, that's going to be 2 cos half the sum sine half the difference. So that means that sine 4x minus sine 2x can be written as 2 cos half the sum, so add the angles and divide by 2, sine half the difference, so subtract the angles and divide by 2. So that can be written as 2 cos 6x divided by 2 is 3x, and then sine 2x divided by 2, which is x. So it then says hence, right? So it doesn't say hence or otherwise. So that means we have to use what we have just found to solve for sine 4x minus sine 2x equals 0. So in other words, if I have sine 4x minus sine 2x equals 0, I can use what I have just found. So instead of writing sine 4x minus sine 2x, I know that that's the same as saying 2 cos 3x sine x equals 0. And now all I have to do is solve. So if I put brackets around this, it makes it fairly obvious what I do next, because these brackets multiply to give me 0, which means the first bracket must equal 0 or the second bracket must equal 0. But of course I'm going to divide everything across by this 2 first before I do that. So 2 divided by 2 is just 1, and 0 divided by 2 is 0. Okay, so what that basically means then is that cos 3x must equal 0, or sine x must equal 0. And now we solve like we did in the last example. We have to be careful of this cos 3x though, because the 3 means I'm going around the circle more than once. I'm going around the circle 3 times, which means then I must use the general solution. So whenever you go around the circle more than once, in other words, whenever there is a number in front of x, we have to use the general solution to solve. And our general solution is where we're going to add on 360 degrees. So that means that 3x is equal to cos inverse of 0. And let's go to our tables. We can see cos inverse of 0 is 90 degrees, but also 270 degrees. So there are 2 possible values here. So that means that we have, I'll just move this page down a bit. That means that we have 3x must equal 90 degrees, or 3x must equal 270 degrees. Okay, but we have to write the general solution before we divide across by 3. That's really important. You have to add on your 360 degrees first, because remember, this function, the 3 in front of the angle is affecting the period. It means that the graph is repeating itself 3 times between 0 and 360. So therefore I have, 270 plus 360. So now I divide across by 3, which gives me 30 plus 120, and 90 plus 120. So this, should be an n there, 360n for our general solution, okay? So this 120 is the period of the graph cos 3x. So the graph is repeating itself every 120 degrees if we were to draw that. So how do we find the solutions? Well, we need to sub in for n equals 0, n equals 1, and n equals 3. So when n is 0, I get x is equal to 30 degrees. And then I have x equals 30 plus 120, which is 150. And then I have x equals 30 plus 2 times 120 is 240. So 240 plus 30 is 270. But that's gone bust. We've gone beyond our domain that we were given in this question. Now, if I was going to 0 to 360, I would include that last answer. But I'm just going to star that for the moment, okay? And then if I do x equals 90 plus 120n, well, when n is 0, that gives me 90. When n is 1, that gives me 90 plus 120, which is 210. And when n is 2, that gives me 90 plus 240, which is 330. And of course, I'm just going to star these last 2 because they've gone beyond 180 degrees. But if I was going to 0 to 360, I would include all of those answers. Okay, so now we are finished with our cos inverse of 3x. We now have to look at sine x equals 0. So when sine x equals 0, that means that x must equal sine inverse of 0. And we saw again from the previous example, if I go to the tables there, I'm getting sine inverse of 0. So we go 0, so that's 0 degrees. And again, 0 gives us 180 degrees. And of course, I can also have 360. But again, that's gone beyond our domain, right? So again, starring that. So if we go back to the start of the question, it says there, it has to be in the domain of 0 to 180. So even though all the answers we have written down are correct, the ones that I have starred here will not be in our final answer. So we therefore say our overall set of solutions, starting at the lowest to the highest, will be 0 degrees, 30 degrees, 90 degrees, 150 degrees, and 180 degrees. And I eliminate this 360, the 210, the 330, and the 270. So 0 to 360, I would include all of those answers, but because we're going 0 to 180, I only have five solutions in my set. Okay? So the questions that you're going to look at based on the sum difference to product then on the sheet are question 11, 18, and 19. So that there, and just put a box around it, are your general solutions for those ones. Okay, so the last type then is our quadratics. So the example we're going to look at for type 4 quadratics is the 2002 higher level question 4b. So the first thing it says is to use the formula sine squared a equals a half times 1 minus cos 2a, which is from page 14 here on our tables. That's this equation here. And we're going to use that to express sine squared a half x in terms of cos x. So basically what that's saying is if we have sine squared a is equal to a half times 1 minus cos 2a, the angle on the right is double the angle on the left, or the angle A is half the angle on the right. In other words, that's why it's called the half angle formula. So if we have sine squared a half x, what that means is if I put that in here, the angle here has to be double, right? So we have A and we have 2A. So if this is half x, then the angle on the right is going to be double, and double a half x is just x. So that's the answer to the first question there. So it then says hence. So hence means we have no other choice. We're going to use what we are given. Now in the Leaving Cert that year it actually said hence or otherwise, but I'm saying hence for the purpose of this example. I want us to use what we have. I don't want any other possible solution. And we're going to use it to solve the equation sine squared a half x minus cos squared x equals 0 in the given domain of 0 to 360. So we're finding all the solutions for the first, second, third and fourth quadrant where relevant. So we're going to take the equation sine squared a half x minus cos squared x equals 0. Instead of sine squared a half x, we're now going to replace it with a half times 1 minus cos x minus cos squared x. I'm going to multiply out my brackets there. And then I have a fraction, so I'm going to multiply across by 2 there to get rid of my fraction. And I'm going to multiply across by minus 2 because I want it in the form of x squared, ax squared plus bx plus c equals 0. And I can see this is going to become a quadratic. So I'm multiplying everything across by minus 2. So that will become minus 1, become plus 1, and it's going to become plus 2 cos squared x. So if I rearrange that, then my quadratic equation that I'm going to solve is 2 cos squared x plus cos x minus 1 equals 0. Okay, so basically that is the same as looking at, say, 2y squared plus y minus 1 equals 0. So there is no difference in solving this algebraic quadratic equation to this trigonometric quadratic equation. In other words, the way in which we proceed is exactly the same. So you have to keep thinking that. What would I do if it was an algebraic quadratic equation? And you do exactly the same thing. So we would take the number 2 and multiply it by minus 1. So 2 times minus 1 is minus 2. What multiplies to give us minus 2 and adds to give us the coefficient of the middle term? So in other words, 1. So the answer must be 2 times minus 1. I'll put back in. So we have 2 cos squared x plus 2, and the middle term is cos x. So in other words, I'm breaking cos x into these two factors here, 2 and minus 1. So 2 cos x minus cos x, and then minus 1. We take out the first two terms and look at the highest common factor, and the second two terms we group and take out the highest common factor. So the highest common factor between the first two is 2 cos x, leaving me with cos x plus 1. Highest common factor between the second two terms is minus 1, leaving me with cos x plus 1. These two brackets are the same again, which is what we always want. So we can take out our highest common factor a second time, cos x plus 1, and that leaves me with 2 cos x minus 1 equals 0. Both of those multiply to give us 0, which means that cos x plus 1 must equal 0, or 2 cos x minus 1 must equal 0. So that means that cos x equals minus 1, or cos x equals a half. And now we solve as before. And if we go to page 13 of our maths tables, we can see cos minus 1, which is 180 degrees. So in other words, if I get cos inverse of minus 1, there is only one possible solution, 180. And then if I get cos inverse of a half, well, if I go to my tables and I look for a half, I can see the answer is 60 degrees. However, the ratio is positive, and we know that cos is positive in the first quadrant and in the fourth quadrant. So therefore, my reference angle is 60 degrees. So again, we're always using our reference angle to find all other possible solutions. In the first quadrant, the answer is 60, and in the fourth quadrant, my rule is 360 minus theta. So 360 minus 60 gives us an angle of 300. So therefore, the two possible solutions here for cos inverse of a half are 60 and 300. So therefore, overall, our solution set between 0 and 360 in increasing order of angle size is 60, 180, and 300 degrees. So the questions that we're going to do on the sheet are going to be 5, 6, 7, 9, and 12. Okay, so you can do all of those questions now that I have marked on the video.